All right, moving on to 6.3, proving identities. This is a section where we start combining our knowledge from other places to form one question. So here we go, example 1, determine the NPVs. 2, verify that the equation actually is or possibly may be an identity. So we can do that either graphically using technology or by substituting one value for x. Finally, prove that the identity is true for all values of x. So let's start with the NPVs. We know that we can't divide by 0. So when I'm looking at cosecant x in the denominator, if that is 0 at any point, then the x cannot be that value. So cosecant x is actually 1 over sine x. Now, 0 is actually over 1, so when I go to reciprocate sine x, I'm going to reciprocate the right-hand side as well. But that's a problem. We don't know what 1 divided by 0 is. That is undefined. Now, if this happens to you on a test, I'd be a little concerned. So how do we check if we made a mistake? Well, let's look at the graphic model of this. So I've already got this on Desmos. So I can't write anything on here, but you can see on the left-hand side, y is equal to cosecant x. And if you look, there's no spot actually on the graph that it crosses the x-axis. So therefore, there isn't any value that x can't be. So when we go back to our question, we can actually say that there are no NPVs. So there's no NPVs. Perfect. Part 1 complete. Okay, moving on to the next one. Verify that the equation may be an identity. So graphically, you could do this yourself. You can put y1 is equal to the left-hand side, and then y2 is equal to the right-hand side. And if the graphs match, then yes, it's possibly an identity. Now, a second method, and maybe the more likely diploma method, is to actually give a value for x. Now here we're allowed to choose. I look at my left-hand side, I see a tan x. Now tan x can be really annoying depending what value you put in there. So I'm going to put a value that I know what it is off of the unit circle. I know that tan pi over 4 is equal to 1. So to me, that's a really nice, easy value. So I'm going to choose tan or pi over 4 as my x value then. So for my left side, and I'm going to actually write that out, let x equal pi over 4, just communicating very clearly what you're doing. So my left side, so tan pi over 4 multiplied by cosine pi over 4, and that is all over cosecant pi over 4. Now we can begin to evaluate. So as I said, the reason we picked pi over 4 is I know, according to the unit circle, tan pi over 4 is actually 1. Again, off the unit circle, cos pi over 4 is square root 2 over 2. Now cosecant, oh, I see, that should be a c there. Cosecant off the unit circle is just the reciprocation of sine, so it's actually going to become 2 over square root 2. All right, we can simplify that a little bit further. This complex fraction I'm going to turn into just a division. So dividing by 2 over square root 2. Now to deal with that, we're going to turn this into a multiplication and reciprocate our second fraction. So you can see this is actually going to turn into a really nice number. So square root of 2 times square root of 2 is 2. 2 times 2 is 4. Well, that actually simplifies to 1 over 2. Now that value means nothing right now. All we know is that the left side, when we substitute x equals 4, is equal to 1/2. So we need to do the same thing to the right side. So let's pick a different color. So then I want my right side. Again, make it very explicit. What are you doing? So now it's going to be 1 minus cosine pi over 4, all squared. And then we can begin to evaluate. So cosine pi over 4 is actually square root of 2 over 2, and that's all squared. Square root of 2 times square root of 2 is 2, and then 2 times 2 is 4. Now that also gets me 2 over 4, which we know already is 1 over 2. So we should check, did our left side equal our right side? Well, it looks like it. We got 1 over 2, and we got 1 over 2. Perfect. Now you need to make sure you answer the question. So therefore, left side equals right side, which means it's verified. So verified for x equals pi over 4. Now, we haven't actually proven that it works for every value yet. We only know it works for x equals pi over 4. We're not going to continue trying to plug in a million different x's. There's a better way, which is what we're going to see in the third part of this question. So prove that the identity is true for all permissible values of x. So this is where we're trying to make the left side equal the right side using our identities. Now I look at the left side, I look at the right side. The right side seems a little bit simpler to me, and the left side seems fairly complicated. So I'm going to try to turn those complicated trigonomic functions into easier ones. So cosecant x and tan x can be, there's all identities for those. So tan x is actually sine x over cosine x. We still have times cos x, and that is all over. Now cosecant x is actually 1 over sine x. And already we can see some simplifications that can happen. The opposite of dividing by cos x is multiplying by cos x, so those both become 1. That already makes a big difference in our equation. So our numerator now is just sine x all over 1 over sine x. I'm going to start going through. It's a little bit faster for how I'm determining my complex fraction. So that does not look how I want it to. So it's just going to become sine x multiplied by sine x over 1. So I just reciprocated that in one step instead of writing it as 2 lines. Now sine x times sine x is actually sine x squared. Now we're very close. If I go and look at my identity sheet, I will find that sine x squared plus cosine x squared is equal to 1. Now if I rearrange that to isolate sine squared, or sine x squared, I'm going to find that it's 1 minus cosine x squared. Well, now I can substitute that in. So I get 1 minus cosine squared x. And if we go and look at what our right side was, it was in fact 1 minus cosine squared x. So perfect. But you need to explicitly say that you have got the correct answer. So therefore, left side equals right side, and it's been verified. Make sure you write that. You want to get 100. All right.